We have so far discussed electric circuits containing capacitors in series and parallel, electric circuits containing resistors in series and parallel, and we saw Kirchhoff's laws for loop circuits. Well, let's combine all that together in one type of a circuit. We will now discuss RC circuits, resistor capacitor circuits. A circuit that contains a resistor and a capacitor is called an RC circuit. Now here I have the diagram of a simple RC circuit. You have a capacitor that has a positive pole and a negative pole. The negative end of the capacitor is connected to the negative pole of the cell, and the positive pole through a cell through a resistor to the positive of the capacitor. Now the circuit shows a resistor R and a capacitor C connected in series. Is that right? This is a series connection across the poles of a cell of EMF E through a switch. Now when the switch is closed, what will happen? Electric charges will flow through the resistor onto the capacitor plate, establishing a current in the circuit. Now tell me, what do you think will happen to the current with time? Will the current remain steady? Well, what happens is, as electric charges continue to flow from the cell to the capacitor plate, the current will start decreasing. You know why? Because initially the rate of flow of charges will be quite high. The current will be very high. As the capacitor gets accumulated with more and more charge, the rate of flow of charge will decrease. That means the amount of charge on the capacitor plate will increase gradually to a maximum, and the current in the circuit, the current flowing through the resistor, will decrease steadily. That is what we would expect. Is that right? Does it make sense? Because the role of the capacitor in that circuit is, when you connect the cell to a capacitor, the capacitor gets charged. And when the capacitor is fully charged, there will be no more flow of charges in that circuit. That means the current initially will be very large because there are no charges on the capacitor plates. Now, as the capacitor plates accumulates more and more charges, the rate of flow of charge will decrease. So when the switch is closed, electric charges will flow from the cell to the capacitor plate, establishing a current in the circuit. The capacitor plate connected to the positive pole gets positively charged, and of course the other will then get negatively charged. Initially, when the capacitor plates have no charge on them, the rate of flow of charges will be large and the current is maximum, and the current then will be given by this. This is the maximum current. I0 equal to E over R. That means the capacitor, there are no charges on the capacitor at T equal to 0. The current then will be E, the EMF, divided by R. This is the maximum current. Ohm's law equation. I equal to V over R. V is the EMF of the cell. So the current now will be, maximum current will be E over R. As the charges get accumulated on the capacitor plates, the flow rate decreases, and so the current will decrease. Alright. When the capacitor is fully charged, there will be no more flow of charges in the circuit, and hence the current will reduce to 0. As the amount of charge on the capacitor plates increases, the current in the circuit decreases. So if you can visualize a graphical representation, the amount of charge will keep on increasing, reaches a maximum, right, sort of asymptotically. And the current will be a maximum in the beginning given by E over R, and it will continue to decrease to 0 after a very long time. Alright, if VR is the potential drop across the resistor and VC is the potential drop across the capacitor, we can apply Kirchhoff's laws, Kirchhoff's second law, in the closed loop circuit. Alright, do you remember Kirchhoff's second law? What does it say? It says in a closed loop circuit, the algebraic sum of the potential drop equal to 0. That means if you add the potential drop across the resistor to the potential drop across the capacitor to the potential drop across the cell, which is the EMF, that sum will be equal to 0. That is what Kirchhoff's law says. So now we're going to apply Kirchhoff's laws in a capacitor-resistor circuit. Can you help me do that? If E is the potential drop across the cell, VR is the potential drop across the resistor, and VC is the potential drop across the capacitor, then E minus VR minus VC will be equal to 0. This is what we call the algebraic sum of the potential drop will be equal to 0. At any given time, if Q is the charge on the capacitor, then the potential drop across the capacitor will be Q over C. Now this is an equation that you're familiar with from the definition of capacitance. The capacitance is Q over V, therefore V equal to Q over C. So the potential drop across the capacitor is Q over C. How about the potential drop across the resistor? The potential drop across the resistor is I times R. Now using those values in this equation, we have the earlier equation we wrote was E minus VR minus VC equal to 0, which is the same as E equal to VR plus VC. That means VR equal to the potential drop across the resistor equal to I times R, and replacing VR and VC, well, let's write IR. What is I equal to? I is the rate of change, the rate of flow of charges. So I times R is dQ by dt times R. Well, let's now rewrite the equation using these values. That is VC equal to Q over C. IR is dQ over dt times R. And use those values in the equation we obtained from the second law of Kirchhoff. That will be E equal to R dQ by dt plus Q over C. And this is now a differential equation. Is that right? This is a differential equation. With what is the independent variable? Independent variable is T and the dependent variable is Q. Now, those who have done an elementary differential equation would know how to solve this. I'm not going to do that for you here. I'm going to give you the solution. Now, the solution of this differential equation, solution will be for what? The dependent variable here is Q, and therefore the solution will be for Q. Q will be given as a function of time. So the solution of this differential equation will give you Q, the quantity of charge, as a function of time. Now this is the solution of that differential equation. Q equal to CE times 1 minus e to the power negative t over RC, where C is the capacitance, E is the EMF of the cell, R is the resistance, and so on. Now what does C times E represent? If you charge a capacitor with a certain amount of charge Q, then we can say that Q equal to CV. Here E stands for the EMF, which is the potential difference. So C times E is the maximum amount of charge on the capacitor plate. You see that? That means when this time is very large, can you tell me what will be the value of this quantity when this T is very large? Now let me ask you this. I'm sure some of you have experience with this. What is the value of limits T approaches infinity e to the power of negative t? What is the limiting value of e to the power of negative t? Well, you know e to the power of negative t is 1 over e to the power of t. And when t becomes infinite, the denominator becomes very large. So this quantity is 0. Limits t goes to 0, e to the power of negative t is 0. So if you look at this equation, it gives you exactly what happens to the quantity of charge. When t equal to 0, what is the value of, when t equal to 0, what is the value of Q? Let me see if your mathematics, your understanding of algebra will let you do this. What is the value of this quantity when t equal to 0? Well, e to the power of 0 is 1. 1 minus 1 is 0. That means at t equal to 0, when you set up this connection and start the clock, at t equal to 0, the amount of charge on the capacitor plate is 0. And as time increases, the amount of charge will increase. Now, and as time increases and as time goes to infinity, after a very long time, the amount of charge will, this quantity will be then 0, and the amount of charge then will be equal to CE, which is the maximum amount of charge. Alright? I hope you're following what I'm saying. In the beginning, when t equal to 0, the value of this is 1. That means Q when t equal to 0 is 0. And when t equal to infinity, it means after a very long time, this quantity will be 0. That will be Q then will be equal to CE. And CE is the maximum amount of charge on the capacitor. So as time increases, the amount of charge will increase. After a long time, it will reach the maximum value. Alright. Since E is the maximum voltage, E is the maximum voltage, the EMF, across the capacitor, CE equal to QF. In other words, that is the maximum charge on the capacitor. I can replace the CE by QF. Why did I use F there for QF? QF is the amount of charge at the end of the charging cycle, the final. So CE equal to QF. Therefore, the solution of this equation is Q equal to QF times 1 minus e to the power negative t over RC. Well, that is the equation for charge as the capacitor gets charged. Now, I'm going to do a little manipulation here. I'm going to say let RC equal to tau. Now, we actually discussed this in connection with Newton's law of cooling, a very similar situation. When RC